Our next topic is equivalent resistance, which often gets abbreviated as REQ. Before we get into the details, though, we have to first define series and parallel circuit elements, because the way that we calculate this is different for each. And we'll start with series. Two elements are in series if all the current flowing through one element must flow through the other. And the easiest way to understand this is to look at a few examples. So here are 4 different examples of different arrangements of resistors, and you have to think about whether the resistors in the example are in series or not. In the first example, we have R1 and R2 right beside each other, and every electron that flows through R1 has to continue and flow through R2. There's no choice. There's no branch. There's no other route that it could take. In the second example, although it's drawn differently, we end up having the same thing. All of the electrons that flow through R1 have to keep going and flow through R2. So the first example and the second example are both in series. In the third example, the electrons that flow through R1 can split. Some of them would go through R2, but some of them would go through R3. So these 3 resistors are not in series. In the fourth example, it's very similar to number 2. All of the electrons that go through R1 have to keep going and go through R2, and they would keep going and go through R3. So all 3 of these resistors, R1, R2, and R3, are all in series in this case. When you have resistors in series, the equivalent resistance is just the sum of the individual resistances. The next thing to look at are elements that are in parallel. And in terms of circuits, 2 circuit elements are in parallel if they are connected to the same pair of wires. And again, it's really helpful to look at examples. So we'll start with a fairly simple example. It's like our flashlight, but a little bit more complicated, where we have an EMF on the left-hand side, and that is connected to a resistor R1, and there's another resistor R2 beside R1. And there's a trick for identifying elements that are in parallel, and the trick basically has you use colors to look at the wires. So if I had a red highlighter, I could highlight the wire that's connected to the EMF until it reaches R1, and that same wire ends up getting connected to R2 as well. Then at the bottom of the EMF, I can highlight the wire coming down, it reaches R1, and then that same wire again reaches R2. Then when I'm looking at these, I can actually label or just list the resistors down at the bottom here, and then I can just use colors to identify. R1 is connected to red on the top and blue on the bottom. R2 is connected to red and blue. And because R1 and R2 are both connected at one side to the red wire and at the other side to the blue wire, therefore they are in parallel. And I could write that as R1 is parallel. I have 2 angled lines here, so that means that R1 is parallel to R2. Now I can rearrange this circuit a little bit, and then I want you to decide whether it's in series or parallel or neither. And I'm looking specifically at the resistors. So I have R1 just like before, and I'm going to put R2 along the top. And it's really tempting for students at the beginning to look for elements that are literally side by side, like in example 1, and you say, well, R1 is beside R2, so therefore they're in parallel. And the standard for this is that elements that are in parallel have to share the same pair of wires. So I can use my color coding again. If I highlight from the EMF to R1, and then I keep highlighting that same wire to R2, and then on the bottom, it highlights in blue, so I have a red wire and a blue wire. And then underneath, again, I can write R1 and R2. And I'll just label the different wires. So R1 is connected to red and blue, and R2 is also connected to red and blue. So even though R1 and R2 are not drawn in the schematic side by side, they are actually parallel because they both are connected to the red wire, and they're both connected on the other side to the blue wire. Now it's time to look at a trickier example of this. So now I have 4 resistors, R1, R2, R3, and R4, and this is similar to the other examples, but also quite different. And when you get a tricky example like this is where highlighting really comes in and can help you out quite a bit. So I'll start with a red highlighter, going from the top of the EMF down to R1, and then across to R2, and then I have to keep going along that wire all the way on the left until it reaches R4. And I can't go any further along that wire. So then I will look at the negative side of the EMF, and that goes down, but then it gets stopped at R3. So the blue wire in this case is quite short. I have a third wire, or at least 3 wires, I should say. So then if I continue from the other side of R3, go up to R1, down to R4, and then up to R2, then I can see that all of the wires are accounted for. And now it's time to take a look. So I will write out the elements. I have R1, R2, R3, and R4. And let's see. R1 has a red wire and a green wire. R2 has a red wire and a green wire. R3 has a blue wire and a green wire. And R4 has a red wire and a green wire. So in this case, R1, R2, and R4 are in parallel. And it's an example where I intentionally set it up with R3 and R4 beside each other so it looks like they would be in parallel. But again, they're not connected to the same wires. R3 is blue-green, R4 is red-green. So in this case, it turns out that R1 is parallel to R2, and R2 is also parallel, as is R1, to R4, because all 3 resistors are connected to the same pair of wires. So the trick to make this a lot easier to get it right the first time and every time is just to color each wire. And then when you have elements, or resistors, I should say, in parallel, because this is specifically for resistors in parallel, the equivalent resistance, Req, is equal to the inverse of R1 plus the inverse of R2, and so on, depending on how many resistors you have in parallel, all to the power of -1. And this is often shown in a different way. Often it would be written as 1 over Req is equal to 1 over R1 plus 1 over R2 plus ... depending on how many you have. I personally prefer the first form of this, where you take the whole thing to the power of -1, because it's a lot easier to enter this in my calculator. Bottom line, you can use whatever you like, but the important thing, actually, and the tricky thing, is to understand which elements are in parallel, so that when you calculate them, you can calculate the correct equivalent resistance.